Hello everyone, my name is Haris, and in this video we're going to be going through the solution of LeetCode number 4, median of two sorted arrays. For this problem, we're given two sorted arrays, nums1 and nums2, of size m and n respectively, and we want to return the median of the two sorted arrays. And for this problem, the overall runtime complexity should be O of log of m plus n. So before we look at the solution, let's understand what a median is. When we're given an array, there are two cases that can occur. The array length is odd or the array length is even. The median is just the middle number in the array when the array is sorted. And since the problem gives us the array already sorted, we can just find the middle number in the array. So for the first example, if we have 1, 2, 3, the middle number is clearly 2. So in this case, the median is 2. However, when we have an array length of even length, we take the average of the two middle numbers. So in this case, we have the middle numbers as 2 and 3. So we take the average of those. So 2 plus 3, and we divide that by 2, and we get a median of 2.5. So since the problem states that we have to come up with a solution in big O of log of m plus n, we simply can't take all the elements in the first array and the second array and add them together and then find the middle number, because that would have a worst case of big O of m plus n, and that would also have a space complexity of big O of m plus n. So the combined median of the two arrays in this case is just the combined array. So if we make an array 1, 1, 2, 2, 3, 3, and 4, and I just combined these two arrays into this one. And since the array length of this array is odd, we can just find the middle number, and in this case the median is 2. So the return, if we're given these two arrays, would be 2. So we have to come up with a solution that's faster. So let's look at an example. So for this example, we're just using the same arrays that we looked at in the previous example. So instead of taking both of the arrays and creating another array with the sorted elements, we can just partition them while we're going through one of the arrays. Then we can use the condition that the maximum of the left from the first array should be less than the minimum right of the second array. And similarly, we need the maximum of the left of the second array to be less than the minimum of the first array's right partition. And the way we create partitions for this algorithm is using binary search, since we want to just split it into two equal partitions and continue the binary search if we do not meet the conditions that I outlined previously. So we can start with the binary search on the first array, and in this case it's x. So in this case, if we're performing binary search, it should just be the start, which is the leftmost value, so 0, and the end, which is the rightmost value, which is 2 in this case. Then we can add these two values together and divide by 2 to get where the binary search will start. So in this case, 0 plus 2 divided by 2 is equal to 1. So we create a partition at 1. Then we can use this formula to create a subsequent partition in the y array based upon the choice of the x array, such that the elements of the partition of the x and the y arrays are equal to the partitions of the x and y on the right side. So since we chose partition x to be 1, we can replace this with 1 and then fill out the formula. And in this case, x and y are the length of the array. So in this case, x is 3 and y is 4. So then we find that partition y is 3. We can go ahead and create a partition at 3 as well. Then if we list out the elements of each of the partitions, we see from X on the left side we have 1, and on the right side we have 2 and 3. And for the Y array we have 1, 2, 3, and then 4 on the right side. We just have to check if these conditions are satisfied. So the max left of the X array, is it less than or equal to the minimum of the right Y array? Well, 1 is less than or equal to 4, so yes it is. But the maximum of the left Y, is it less than the minimum of the right X array? Well, 3 is not less than or equal to 2. So this condition fails. That means we have to go ahead and perform binary search again on the first array, in this case X. Now if we perform binary search, we want to move the start index to the right side. But if we move it to 1, then we'll actually get the same result, since the start plus the end divided by 2, in this case integer division, will still give us a partition X of 1. And that will result in the same partition. So if we continue for a second iteration, we'll actually see that start and end are both 2. So if we make the partitions on the arrays, and then write down the elements that are formed by the partitions, so in this case 1, 2, and 3, and then we have 1 and 2, and 3 and 4. And these are just coming from the array partitions. So then we can go ahead and check the conditions. So is the max left X less than or equal to the minimum right of Y? And 2 is less than or equal to 3, so this condition passes. Similarly, the max left of Y, is it less than the minimum right X partition? Well, 2 again is less than 3, so yes, it passes that condition. And since both of the conditions are fulfilled, that means we have found the 4 elements in the middle of the 2 combined arrays. Now finally, if we're dealing with an odd number of total elements between X and Y, then we can simply take the maximum of these two. And since they're the same, the median is 2, as we concluded previously. However, if the total number of elements is even, we can just take the maximum from these 2 elements and the minimum from these 2 elements, and that will give us the exact same result. Also, it's worth mentioning that if we ever get an empty array on one of these sides, which is possible if the total number of elements is even, well then we can just consider positive and negative infinity as those values. So let's say we have values of minus infinity and positive infinity to the left and to the right of the array. This will make more sense when we write out the code, but it's good to keep in mind for the edge cases when we're thinking about the solution. So hopefully the intuition is clear with regards to the binary search that we're performing on the smaller array, and we'll always want to perform it on the smaller array since it's the minimum of the X and Y values. And then we have found a solution that is running in big O of log m plus n in the worst case, and has a space complexity of O of 1. With that being said, we can go ahead and write the code for this solution. Okay, we're on LeetCode and we can start writing the code for the solution. As I mentioned previously, we always want to perform one binary search on the smaller of the 2 arrays, and we'll always make that the first array, in this case for simplicity. So we can just write if the length of the nums1 array, if it's greater than the length of the nums2 array, then we'll just swap them. So nums1 and nums2 is equal to nums2 and nums1. Then we can establish the 2 variables, the start and the end, for the binary search, as well as the x and the y values that correspond to the length of the arrays. So the start and the end will be 0 and the length of nums1. And we can say x and y will be the length of nums1 and length of nums2 respectively. Then we can perform binary search on the first nums1 array. So we'll say while the start is less than or equal to the end, we'll create the partitions. So partition x is going to be the start plus the end. And we also want to use integer division since it's indices and we can't have a decimal number as an index. So just to make sure, we'll use integer division. And similarly, we'll write partition y as x plus y plus 1, which is the formula that we used previously. And we'll divide this by 2 and then subtract partition x. Then we can go ahead and calculate the max left of the x array, the minimum right of the x array, the max left of the y array, and the minimum right of the y array. And these all correspond to the ends of the partitions that we create. So we can say that max left of x, we'll say that this is equal to minus infinity. So as we discussed, if there are no elements in that partition, we have to use positive or negative infinity. And since this is the x partition on the left side, we'll write minus infinity. And we'll only say that this is true if the partition x is equal to 0. Otherwise, we'll just partition it with the last element. So it's the length minus 1. Similarly, we'll do the same for the right hand side of the partition, but in this case, we're having positive infinity since this is the right side of the partition. And we'll say if partition of x, if it equals its length, that means we've reached the end of the partition index. And then we'll take the index from nums1 at partition x. We can do something very similar for partition y, so I'll go ahead and copy this and just change the x to y's, since it is very similar in the way that we're getting the partitions. We're just using the values that we've defined, and also make sure to change it to nums2 since we're dealing with the second array. Then we want to check for the conditions after we've found the values for the max and the min of the partitions. So the two conditions that we mentioned were if the maximum of left x, if it's less than or equal to the minimum of the right y, and the maximum left y is less than or equal to the minimum right of x. And then finally, we can say if x plus y mod 2 is 0, and this indicates an even number of total elements, then we need to return the maximum of max left x and max left y. So it's the two left partitions plus the minimum of min rights x and min rights y. And then we divide both of these by 2. Otherwise, we know that we have an odd number of total elements, so we can just return the maximum of the two left partitions. So return max left x and max left y. Otherwise, if the maximum left of x is greater than the minimum right of y, we want to move the partition to the left since we know that we're too far to the right. So then we'll say end equals partition of x minus 1. Otherwise, we know that we're too far to the left, so we'll say start equals partition of x plus 1. And this is just a basic binary search when it comes down to it. So we can go ahead and run the code to see if it passes. And the code is accepted, so we'll go ahead and submit it. And it passes all the test cases. So this is the solution to the problem, and it's solved in O of log of m plus n time with O of 1 space complexity. So hopefully the video helped you and you learned something, and I'll see you soon.